Dear students, I am Ramesh, chemistry faculty from Vidya Mandir Metric Higher Secondary School, Uttangarai. Last session we discussed about mesomeric effect and resonance effect. And in this session we may discuss hyperconjugation and its application. Now, what do you mean by hyperconjugation? Here, the delocalization of electrons of a sigma bond. Delocalization of electrons of a sigma bond, which is known as hyperconjugation. So it is delocalization of electrons of sigma bond is known as hyperconjugation. Hyperconjugation. And it is a special stabilizing effect. So it is a special stabilizing effect. Stabilizing effect. And here it is due to the pi bond delocalization of adjacent empty non-bonding p orbital. So here the delocalization of electrons of sigma bond to adjacent empty non-bonding p orbital. Non-bonding p orbital. So here the delocalization occurs between sigma bond and p orbital. Then it is a permanent effect. It is a permanent effect. So here hyperconjugation is a permanent effect. Only electromeric effects are temporary. And this hyperconjugation is otherwise known as Baker-Norton effect or no bond resonance. So it is otherwise known as, one is no bond resonance. No bond resonance and are called as Baker-Norton effect. Baker-Norton effect. So sometimes they may ask, what is that no bond resonance or what is that Baker-Norton effect? It's nothing but hyperconjugation. Okay. Now, what is the condition of this hyperconjugation? So we are take the next condition of hyperconjugation. And the first condition, the organic molecule which contains sp2 hybridized carbon. So here the organic molecule must contain sp2 hybridized carbon atom. sp2 hybridized carbon atom, then only hyperconjugation is occur. And the second condition, here the at least one carbon hydrogen bond which is bonded with this sp2 hybridized carbon. And first here, if it is sp2 hybridized carbon, where the sp2 hybridized carbon, and we may take that alkene. What is that? Alkene. Alkenes are sp2 hybridized carbon. Suppose if you are taken, that is CH2 double bond CH2. And I am already told you here, for a carbon, how will you identify hybridization? Hybridization of carbon compounds is easily identified like count number of sigma bond surrounded by the carbon. Now, the first carbon, number of sigma bond. What is that? Here 2 sigma bond with 2 hydrogen, and here 1 sigma bond and 1 pi bond. So, this carbon is surrounded by 3 sigma bond. So, it is sp2 hybridized. And here also, here 1 sigma bond and pi bond and 2 sigma bond attached with that hydrogen. So, it is also sp2 carbon. So, alkenes are mostly sp2 carbon. And the second one we may take, that is carbocation. Carbocation. And carbocations are by loss of 1 electron from the carbon, then it is also sp2 hybridized. For example, we are take, that is carbon and hydrogen, hydrogen and hydrogen, and it is carbocation, methyl carbocation. And any carbocation is surrounded by only 3 covalent bond. So, if it is a 3 covalent bond, then it is sp2 hybridized. sp2 hybridized. And also, we are taking that is a free radical. Free radical. So, free radical is also sp2 hybridized. What is it, free radical? Here we may take methyl free radical, that is CH3 single dot, and carbon, hydrogen and hydrogen and hydrogen, then 1 electron. And free radicals are considered as a neutral, and so that this electron is not considered, and it has only 3 covalent bond, so that it is sp2 hybridized. So, what is the first condition of hyperconjugation? And here a carbonic molecule must contains sp2 hybridized carbon. sp2 hybridized carbon. Now, the second condition here, an organic molecule contains at least one carbon hydrogen bond attached to the sp2 hybridized carbon. sp2 hybridized carbon. So, sp2 hybridized carbon. So, here at least one CH bond is attached with sp2 hybridized carbon. Suppose here that is C bond H may be attached with, that is a alkene, that is CH double bond CH2. Now it is sp2 carbon is attached with CH bond, or it may be attached with carbocation or free radical. So, here the CH bond, at least one CH bond is attached with sp2 hybridized carbon. And the third one here, the atom or group which contains lone pair is attached with sp2 carbon. So, the atom or group is atom or group with contains lone pair, attached to sp2 hybridized carbon atom. So here an atom or group which contains lone pair. Suppose we are taken nitrogen or oxygen or the cyanide group. These are all containing lone pair. Nitrogen has 1 lone pair and oxygen has 2 lone pair. And in the case of cyanide, this nitrogen has 1 lone pair. These are the groups is directly attached with this sp2 carbon. Then the hybridization or hyperconjugation is occurred. So the first condition, What is it? It contains sp2 carbon, and adjacent to sp2 carbon, it has CH bond or nitrogen or oxygen with lone pair. Now, we may take the examples of hyperconjugation. So, we are taking the first example, that is propylene. So, we are taking the example. Example 1. Then, propylene molecule, that is CH3, then CH, double bond CH2. Propylene molecule. Now, in propylene molecule, what is that? Here it is sp2 carbon. sp2 carbon. Now, adjacent to sp2 carbon, which contains CH bond. So that these molecules undergo hyperconjugation or resonating effect or Baker-Norton effect. Now, we may take here carbon and hydrogen and hydrogen and hydrogen. And here that is CH bond, C bond, H, and double bond C, H, and that H. Now, we may expand here. Now, what is that hyperconjugation? The sigma bond delocalization with this sp2 hybridized carbon which has empty and non-bonding p orbital. So, this sigma bond get delocalized. Delocalized means it will be moved. It is not stable at a particular place. Then it is known as delocalization. It is continuous moving. So, sigma bond delocalization is nothing but a hyperconjugation, and it is adjacent to vacant or empty p orbital. So, it will be get delocalized here. Then we may get the canonical forms. So, what is the canonical form? Here carbon and hydrogen positive and bar hydrogen and bond here hydrogen, this one. And it will be get that a double bond. Here there is a double bond, and here it has C bond H. And so this carbon has highest electron density, so the bond is moved here. So carbon, and it is a negative charge, and here hydrogen and that hydrogen. So we may get the first canonical form. First canonical form. So it is the first canonical form. And there is a possibility, why not this hydrogen and this hydrogen? So we are getting that here this carbon hydrogen and now this carbon and hydrogen. So we may get the another canonical form, that is carbon and hydrogen, and here H plus and bond hydrogen, and it is double bond C bond H and C minus and H and that H. So that we are getting this one. Another one, that is a second canonical structure. Now, why not this bond? This CH bond is also get that resonating structure, involve resonating structure. So we are getting that carbon and bonded with hydrogen, here also bonded with hydrogen, and it is no bond. Now here there is a bond and carbon and hydrogen and C, H and H getting the negative. So it is third canonical form. So hyperconjugation leads to resonating structure. We are getting the three resonating structures for propylene. Now in this case, here there is no bond between carbon and hydrogen. Here also there is no bond between carbon and hydrogen. Here also there is no bond between carbon and hydrogen, and it has only delocalization of the sigma electron to sp2 hybridized carbon, which contains vacant or empty p orbital. vacant or empty p orbital. So here it is get delocalized and this bond get delocalized, and here this bond get delocalized to sp2 carbon. So it is sp2, and here also it is sp2, and here sp2 carbon. So delocalization of a sigma electron to sp2 carbon is nothing but hybrid conjugation. So there is no bond between carbon and hydrogen in all canonical form, so that they are called as no bond resonance. No bond resonance. So why it is called as no bond resonance? Hyperconjugation, there is no bond between that. There is a CH bond. So here there is a CH bond, there is no bond. So it is always known as Baker-Norton effect. Now we may take that the second example, and it is ethyl carbocation, CH3 CH2 plus ethyl carbocation, and it will involve hyperconjugation or not. First check it out, and one is sp2 hybridized carbon. Now here we are taking that is a carbon, hydrogen and hydrogen and hydrogen, and here carbon and here hydrogen and here hydrogen, there is a positive charge. Now this is sp2 hybridized carbon, correct? It has only 3 sigma bond, so it is sp2 hybridized carbon, and it has carbon and CH bond. So adjacent to sp2 hybridized carbon, there is a presence of CH bond, at least one CH bond, then the molecule will undergo hyperconjugation. Now we may take that this sp2 hybridized carbon for that this carbon. Suppose we may take that carbon, the atomic number 6, and its electronic configuration, it is 1s2 and 2s1 and 2px1 and 2py1 and 2pz1. It is in excited state. Excited state. So the valency will be 4. Now carbon getting that positive charge. So one electron will be lost. So we are getting that here it is 1s2, 1s2, and it is 2s1, and it is 2p orbital, and here 2px1 and 2py1. Now it will be undergo hybridization. So what is the hybridization here? It is sp2 hybridization. So it will undergo sp2 hybridization, so that here it is 1s2 and sp2 hybridized orbitals are 3, then here 1 and 1 electron and 1 electron, and here it is 2pz orbital, and it has vacant or empty 2pz orbital. Now we may take the shapes of sp2 hybridized. So we may take the sp2 hybridized orbital. So the sp2 hybridized orbital, and it is sp2 hybridized orbital. We are take this is the sp2 hybridized orbital. So here 1 electron and 1 electron and 1 electron, then it is sp2, here also sp2, and here sp2. It will be occur in one plane. Now the 2pz orbital, which is perpendicular to this sp2 hybridized orbital, then it is 2pz orbital, which is vacant or empty. Now this vacant and empty p orbital is delocalized with the CH bond electron, so that we may take that here it is CH3 and CH2 plus, and so this CH2 as this vacant p orbital, so that here this is sp3 hybridized. It has 4 bonds around a carbon. So it is sp3 hybridized. And if it is sp3 hybridized, then it is a tetrahedral in shape. Correct? It is a tetrahedral in shape. So it is sp3 hybridized. sp3 and sp3 and here sp3 and here sp3. Now each one has bonded with hydrogen, so that here 2 electron hydrogen and here 2 electron by hydrogen and here 2 electron carbon hydrogen and here 2 electron and carbon hydrogen bond. So it is bonded with this sp2 carbon, and this sp2 carbon has empty 2pz orbital. So this electron is delocalized with this empty 2pz orbital, which is known as hyperconjugation. So the CH bond, it is nothing but it is carbon and here hydrogen. So this bond. So the CH bond is delocalized with the empty 2pz orbital, which is known as hyperconjugation. So we may take the resonance of ethyl carbocation. So here carbon, hydrogen and hydrogen and hydrogen, and it is carbon and hydrogen positive. So this bond, the sigma bond delocalized here, sigma bond delocalization occurs. So we are getting that the resonance structure, that is carbon and hydrogen bond hydrogen and here hydrogen and here double bond CH and that H. And this hydrogen is also undergo resonance stabilized. So we are getting one more structure, that is carbon H plus bond hydrogen double bond CH and that H. And it is also undergo resonance hybridized with this hydrogen, so that carbon bond hydrogen and H plus double bond C and H and that H. So it is ethyl carbocation canonical forms. So that these are known as Baker-Northern effect or no bond resonance. And we are taking the third example, that is CH2 double bond CH is attached with chlorine, which has highest electronegative atom and which contains lone pair. So the sp2 hybridized carbon is attached with atom or group which contains lone pair. This is also undergo hyperconjugation. Now what will happen here? We are getting that the bond movement, the lone pair is moved towards that sp2 carbon, and it is like a CH bond, so that the bond is going here. So we are getting the resonance stabilized structure, that is CH2 minus bond, that is CH, and here double bond, then it is Cl, and it has positive and 2 lone pair. So we are getting that hyperconjugation. So here the lone pair of electron undergo delocalization. So the first condition, sigma bond undergo delocalization with sp2 hybridized carbon, or lone pair may undergo delocalization with sp2 hybridized carbon. Then it is known as hyperconjugation. Now the applications of hyperconjugation, and the first application, it will be gives the stability of carbocation. So it will be gives the stability of carbocation. And you know that the carbocation stability order. What is the carbocation stability order? And here that is Me3C. That is trimethyl carbocation, that is tertiary carbocation is more stable. Then that is Me2CH, it is secondary carbocation. And that is MeCH2, that is primary carbocation. and CH3, it is methyl carbocation. Methyl carbocation. So all are carbocation. So here carbocation order stability, that is tertiary, secondary, primary and methyl carbocation. Okay, here listen. Here we may explain it with the hyperconjugation, and we are taking, that is tertiary carbocation first. Here it is CH3 thrice C plus. This is methyl carbocation. And we may take this methyl carbocation, and here it is carbocation. It is attached with, what is that? Carbon, and here there is a carbon, and here there is a carbon. And it is attached with 3 hydrogen. Here also 3 hydrogen. And here also 3 hydrogen. Correct? Now, this is sp2 hybridized carbon. Now, the sp2 hybridized carbon is attached with the CH bond. Will undergo, there is a possibility of hyperconjugation. How many hyperconjugative or canonical forms are possible? And it may be moved here, say may this one and this one. And also another 3 hydrogen CH bond, and here also 3 CH bond. So it is totally 9 hyperconjugative canonical forms are possible. So 9 hyperconjugative canonical forms are possible. So if it is a highest hyperconjugation structure, then the stability is the greatest. So among this, tertiary carbocation is more stable than secondary carbocation. If we are considered secondary carbocation, how many conjugative structures are possible? If we are taking that secondary carbocation. Now, it is a secondary carbocation, that is a CH, and it is a secondary carbocation. And in the case of secondary carbocation, that is the carbocation is attached with that 2 carbon, and here the carbon, and here carbon. Each one carbon contains 3 hydrogen. And hydrogen, and hydrogen, and hydrogen. So it is the secondary carbocation, and it is sp2 hybridized carbon. Adjacent to sp2 hybridized carbon, there are, what is that? CH and CH and CH. So 3 CH, and here 3 CH. So 6 hyperconjugative structures are possible. 6 hyperconjugative structures are possible. So if we are taking that tertiary, then we are getting 9 hyperconjugative, so which is most stable. Then secondary carbocation, it has only 6 hyperconjugative. Now if we are taking that, the third one, that is primary carbocation, and example CH3 and CH2 plus. Now we are taking carbon, hydrogen, and that hydrogen positive, and it is attached with C, H, H, and that H. Now it is sp2 hybridized carbon. Adjacent to, there are 3 CH bond. So in this 3 hyperconjugative structure, 3 hyperconjugative structures are possible. So 3 hyperconjugative structures, so that it is the least stable than that of secondary and tertiary. If you are taken, that is the methyl. Here it is a methyl carbocation, and in the case of methyl carbocation, and here hydrogen and hydrogen and hydrogen, and here it is sp2 hybridized carbon. And adjacent to this sp2 hybridized carbon, there is no CH bond, so that it does not involve hyperconjugation, so that it is least stable. Now, the second application, it explains the stability of benzyl carbocation. benzyl carbocation. Now, we may compare the four compounds. We are taking the first compound. This is the benzyl carbocation and it is attached with CH3 thrice C. CH3 thrice C. And the second compound, it is CH3 twice CH and it is attached with benzyl carbocation and here CH2 and it is benzyl carbocation and it is A and it is B. Now the third compound, it is CH3 CH2 bond this benzyl carbocation, then it is CH2 plus. Now here it is CH3 and we are taking benzyl carbocation and it is D and that it is C. Now according to plus I effect, we may compare all those A, B, C, D and it has greater plus I effect and it is lesser, that is tertiary and that secondary and primary and that methyl. So which one is most stable according to plus I effect? Then it is A is greater than B and that C and that D. So it is most stable. But the observation, the concept is wrong. So it will be explained by this hyperconjugation. Now we may take that hyperconjugation. And in the case of hyperconjugation, and we are taking this. And here it is sp2 hybridized carbon. sp2 hybridized carbon. And adjacent to sp2 hybridized carbon, there is no CH bond. So that there is no hyperconjugation. No hyperconjugation occurs in this one. So A is very least. Now the second one, it is sp2 hybridized carbon. sp2 hybridized carbon. So that adjacent to sp2 hybridized carbon, there is one CH group, so that there is a possibility of one hyperconjugative effect. And here there are sp2 hybridized carbon and here there are two C bond H groups. So two hyperconjugative effect is possible. Now in this case, what is that? It has three hyperconjugative. Three hyperconjugation is possible. For example, we may take the option D. So we are taking that option D, that is carbon, hydrogen and hydrogen and hydrogen. It is bonded with the phenyl group and here it is CH2 plus. CH2 plus. Now it is sp2 hybridized carbon and it is adjacent to sp2 hybridized carbon, there is a CH bond. So delocalization occurred, so that this bond is going to here and this bond is going to here. So what is it? We are getting, that is carbon, no bond resonance and bond hydrogen and hydrogen and double bond. Here we are taking undisturbed bond and delocalization and here double bond and CH2. So positive charge is somewhat neutralized. Now same way this hydrogen and this hydrogen. So in this case we are getting three canonical form, so that it is the D is more stable than that of C and that B and that A, and it is reverse of plus I effect. So by plus I effect it is not able to explain, but by hyperconjugation we explained this. And the next one, the third one, the stability of alkene. Stability of alkene. More substituted alkene is more stable. So here take more substituted alkene are more stable. More stable. Listen, if you have taken carbon double bond carbon and all are hydrogen, alkyl group. Substitution all are alkyl group. Then here CH3, 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 CH3. So 3, 6, 9, 12. So 12 hyperconjugative effects are possible. So it is more stable. Then it is next to here carbon, R group, double bond C and R under that hydrogen. So it has 9 hyperconjugation. And that next one carbon double bond carbon and here hydrogen and hydrogen R group under that R group. And the next one we are take here, that is carbon double bond carbon and here R under that R under that H and H, that is transalkene. So transalkene is more stable. Then cisalkene, carbon double bond carbon and here R group and R group, hydrogen and hydrogen. So it is cisalkene or more stable. And the next one, what is that? Here carbon double bond carbon and here R H and that H, and there is no substitution, it is least stable. So carbon double bond carbon, hydrogen and here hydrogen. So we may explain the stability of alkene. Dear students, in this session we explain hyperconjugation in detail. Go through your textbook and the NCERT book. Thank you.